Welcome back to ThinkTech. I'm Jay Fidell. This is the Community Matters series. Today we're going to talk about why wildland fire science has become critical and will become even more critical going forward. Climate change makes these fires more and more threatening. And for our guest, we have Francis Fujioka. He's a retired meteorological researcher for the U.S. Forest Service. And we need to know about, what he has done, what he has thought about, the systems he has made over his career to determine, how the science affects wildfires and firefighters and how it will affect them going forward. Welcome to the show, Francis. It's nice to have you here.
Thank you. Aloha kako to you and to all of us who have joined us today.
Why do I feel you're a local guy?
I was born and raised in Ewa, went to elementary, intermediate school there, high school in Waipahu, University of Hawaii, got my bachelor's and master's degree there. And I started my Forest Service career in Honolulu before I moved on in 1977 to California.
So why did you enter that field? What was it about that field that attracted you? This is way back when already.
Totally backed up into, didn't know what I was getting into, Jay. In fact, at the University of Hawaii, this is back in 1960, late 1960s, early 1970s, when I was a graduate student there. There was a new technology called computers. It occupied one whole wing of the Hawaii Institute of Geophysics on the campus at Manoa. And so I got interested in that. In fact, I used the computer there to, in my master's research with the Department of Meteorology. And so when I finished with that, actually, I was interested in air pollution research because that was what my master's thesis was about. So I went to California looking for a job in air pollution research. Long story short, one of the places I visited was the Riverside Fire Lab, which belonged to the U.S. Forest Service in Riverside, California. Applied for a job there. They didn't hire me there, but they sent my application instead to Honolulu. And lo and behold, some 5 months later, I was back working for the Forest Service in Honolulu.
And this was, before Al Gore, wasn't it? You were interested in environment and climate change before Al Gore, all right?
It was about the time that President Nixon signed the Endangered Species Act. So, environment was definitely on people's minds. But I didn't even know that the Forest Service had a presence in Hawaii.
But then you had a big effect on that because you developed a fire danger rating system, and that was special for Hawaii. Can you talk about how you applied your education to create that system and to create a variation of that system that was appropriate for Honolulu and for the state of Hawaii?
When I hired on with the Forest Service, I didn't know a thing about it. And I think the Forest Service hired me for my computational skills and what I learned at UH. And so the scientist that I worked with in the Honolulu office was a gentleman named Bob Bergen. And Bob and I actually started in fire danger research in Hawaii together. And Bob went on to the Forest Service Missoula Fire Lab in Missoula, Montana, where he did even more work on the National Fire Danger Rating System. So I just did what Bob asked of me in terms of the computing, but I got to learn as the years went by about the science and the technology. And so Bob left for the research in Missoula, and so I was put in charge of the fire danger rating system in Hawaii.
Which was different than the National Fire Danger Rating System. And let me make a wild guess to say that a fire danger rating system takes data from wherever it can get it, and it gives you a readout. of the danger in your area and the geographical area you're pointed at. And it tells you whether you're likely to have a fire there, the size, the intensity of the fire, and it helps firefighters to prepare for the fire, to get staffed up for the fire, and to put the fire out. How much of that is correct? That's a wild guess, Francis.
Well, that's a very good guess. So let me expand on that with my first slide. So if I can have that. So I'm assuming that people can see that slide there.
Mm-hmm.
And what that shows you is that we start with weather, fuels, and topography data. And we feed that data into a mathematical fire spread model that was developed at the Missoula Fire Lab. And it spews out information about ignition, spread, and the heat release characteristics from the fire, given the weather, fuels, and topography. So that's the basic science behind it. And there's a lot that went into it. So when we started this project in Hawaii, and this was, I joined in the Forest Service in 1972. Prior to that, the Hawaii Division of Forestry had asked the Forest Service to come up with a system to systematically assess fire danger statewide. And actually, the National Fire Danger Rating debuted at about that time. So it was placed on Bob Bergen's head to bring this system to Hawaii in 1972. And they hired me to help Bob. And over that time, we worked with the Forest Service Riverside Fire Lab, which was the other of actually three national fire labs that the Forest Service had at that time. The first being in Missoula, second in Riverside, California.
Let me go back to your first slide for a second, Francis.
Sure.
Slide, you have three pieces of data being entered. One is weather, one is fuels, one is topography. Okay, and I'm just imagining how your computer model would get that data and actually interpolate that data. So weather you can get from the Weather Service, right? And it's downloadable. We know from SOEST, many interviews at SOEST, that kind of data is easy to get. It's free from the government, so we know what weather is. Fuels, it sounds like fuels means what do we got there in the woods? We have brush, we have trees, we have material on the ground. I suppose we could have residences there too. It's all the kind of stuff that could burn, right? That's fuels. That means you have to eyeball it, right? You have to go out into the woods. You have to look and see. Or is there some way to determine fuels by computer data downloaded?
Let me get to the next slide to answer that question, or
Okay.
the series of questions, actually. So what we did for the fire danger rating system is to look at each island and try to identify fire danger zones that would be classified according to fuels, weather, and topography. And within each fire danger zone, we located at least one weather station. So we could use each of this data in our mathematical fire spread model to describe the fire danger characteristics, namely ignition potential, spread potential, and energy release potential. And let's see.
So that means you have to assign a value to the weather. If it's going to be hot, for example, or if it's going to rain, that's on the other side of the equation. And to the fuels. If the fuels are particularly flammable, you're going to have to assign a value to that. And the topography, I'm not sure how it would work, but if the topography is low, you assign one value. If it's high, another value. If it's rolling hills, another value. So it sort of depends on assigning these values. And then when you get these values together, there's an algorithm, right, for the middle part of that first chart to say, well, if we have this combination or that combination, we reach a fire rating, a danger fire rating of a certain metric. So what's the scale for that, Francis? Is it 0 to 10, 0 to 100, A to Z? How do you actually measure at the end of the day?
It varies, Jay, according to as to whether you're talking about fuels, weather, or topography. Now, topography is actually the data that we can resolve with the highest resolution. So we can take a map, and at 30-meter intervals, we can identify the elevation over the course of that map. And from this elevation data, we get slope information, which is critical to how a fire spreads, because if it's burning upslope, it'll burn faster than if it burns downslope.
Okay, that's a big learning point.
Right.
It's burning upslope. So if you have more slopes, and then you have to match that with the weather to see which way the wind is going to blow, upslope, for example, you're going to have a fire that moves faster.
Exactly, and that's what the fire spread model takes into account.
Okay, so this is developed in Missoula. It's developed in various places in the country. It's the United States Forest Service, and the question is, why is this here in Hawaii different from the whole continental U.S.? What did you find that made the variables, maybe obtaining the data and the algorithm different here in Hawaii?
Well, the advantage of using a mathematical model like one that was developed in Missoula is that the model describes, as best as the scientists could put together at that time, the physics behind combustion in the wildlands. And so if we could bring to that model data about the characteristics of the vegetation, about the weather aspects that influence, in particular, the moisture content of the vegetation, and if we could bring information about how winds behave, both in terms of speed and direction, at any given site, then we could do a better job of defining or quantifying the spread and ignition and energy release potential there. So the model,
those data go in. They're universal data. In other words, wherever you are in the world, you put those data in. What it sounds like to me in this conversation, anyway, is that the algorithm by which you interpolate and analyze that data, that's the part that would be different for Hawaii. Am I right?
No, it's the algorithm. The model. Let me say the model can be used anywhere with different weather, vegetation, and topography data.
So it's the data that's different here.
That's correct.
Okay.
The data makes the description of those fire danger characteristics different from place to place, whether you're talking about different places in Hawaii or Hawaii versus California or things like that.
And the scientist, the model, the whole system is working all the time because you're looking down the road to find out what the fire danger is. In other words, every time the data changes, conceivably, the rating would change for the danger. So you're looking at the models that are you're looking at the weather, the fuels, the topography all the time. And the rating, you could watch the rating change.
That's correct. And the other complex question we face here, or the challenge we face here, is trying to push that information out into the future as far as possible to make the assessment of fire danger easier for the fire managers that are responsible for placing firefighting resources where they would be needed in the future. So when we started
somewhere, you have a computer which reads out whatever the value, the rating is, okay? And you can look at it all the time. It's going to be dynamic, and you can tell what the rating is today as for the future, however far away, far along the path you can see. What about the fire management guys? Do they have the same computer? Is this real time for them? Did they know what the fire danger rating is for a given area? How do they get that from you?
Let me get to that answer with a subsequent slide I have. Let me first of all pull up the next slide. So this slide answers the question that you just posed to me, Jay. So the fire danger rating system that we ended up with before I retired in 2011 looked like this slide here. So this is part of a geographic information system which would show fire danger rating or aspects of it. And this application was housed at the Pacific Disaster Center in Kihei, Maui. So any of the firefighters with access to the internet could get on this website and pull this information down using this GIS software. And I think I have another example. Can I get the next slide? So the weather information we used for this system was driven by forecast data from the National Weather Service. And that's an example of what you're looking at there. So the NWS provided us with temperature, relative humidity, precipitation, wind direction, and speed, etc. All of that went into our fire spread model. And from that, we produced these fire danger parameters that I mentioned before. So let me go to my next slide. The problem in Hawaii is that the changes in topography are so acute that they can easily affect wind behavior in unpredictable ways, at least as far as what the computer models that the National Weather Service used are able to see or not see. In other words, it's a question of resolution, because typically the models that, at least the models that were used by the Weather Service when I was there were global models. So they provided weather information at tens of kilometers distance between each grid point. Mm-hmm. And so I worked with Professor Yiling Chen at the University of Hawaii in the Atmospheric Sciences Department. And we came up with a model like this one that is able to resolve weather down to grid distances of 1.5 kilometers. So that's
you can see where the danger was. You had a geographical parameter.
Correct. And so we could see these highly resolved wind fields, which would in fact help us to determine the fire spread potential more precisely.
Hey, I'm thinking of a disaster movie now, if you don't mind, sort of stretch it out into fiction. So I'm in Kihei there, and I look at the screen, and the screen shows me that from yesterday till today, the danger rating has gone up, precipitously, and it's now double or triple what it was a few days ago. What does that lead me to do? Now I have that information, and as you say, it's geographical, so this could be on any island. So, but Kihei will know any island because you're giving him information on all islands. So, query: what does the guy behind the screen do at that point in order to react to the danger?
Well, what they do typically in using the National Fire Danger Rating System is they look at the numbers that are forecast for tomorrow or the numbers that they see today, and they compare that with the historical or the statistical numbers for that location, maybe for that time of the year in the past. And so if it's way above what those average values would be for that place and time, then they staff up. They add people anticipating fire problems in that particular place and time.
And then they can tell from the location and the terrain how fast it's moving, how serious it is, and what it's likely to burn over a period of time. But one thing you didn't mention, Francis, and I really am so curious about this. You gave us three parameters of data. One was the weather, one was the fuel, and one was the topography. But it seems to me there's a fourth. Sure, you've thought of this. There's a fourth parameter, and that's whether it's already burning. Because if it's already burning, the danger rating systems are going to go through the roof, right?
Well, in fact, with the fire danger rating, we assume that if there's a fire there, this is how it's going to spread. This is how hot it's going to burn. But you're right. I mean, when there is an actual fire at any given location, we actually don't use the fire danger rating system. We turn into another mode, which is, you can term fire behavior modeling. And so at that point, we need data at an even finer scale of resolution. Now, in the fire danger rating system, we talk about vegetation in 1 kilometer squares. But when we have an actual fire going, now we have to resolve the vegetation data even finer. So typically in that case, and I've done research with these fire behavior modeling systems as well. We have one called Farsight in the Forest Service. We resolve vegetation down to 30-meter intervals.
Okay. So you can tell. How do you learn that a fire is actually burning? Is that, people on the ground, the fire department, that area, the police? How do you find out?
That's how it's typically done. And for, a place like Hawaii, that's not as much of a challenge as it is here in California, because we have vast expanses of forest area here, and you can get a fire where there's nobody around. And in fact, a serious problem that has occurred in recent times is we have power corridors going through forested areas. And when we have high wind events, these power lines can arc and cause fires. In fact, that they were responsible for a huge fire that we had in Northern California. So,
would you say that the presence of power lines in a given area is a factor in determining risk?
Absolutely, in California, because it used to be that when I first started in this, the people that were most interested in fire potential were those folks that lived near or in what was called a wildland urban interface, where you could go into your backyard and see a forest or wildlands there. Now, you can live in the middle of San Diego and be affected by fire potential. Why? Because in the event that there is a potential for a power line to start a fire, if you're in San Diego Gas and Electric can shut off the power, because they'll say, we've got a fire threat. We don't want to assume liability for it. And so even in the middle of San Diego, you could be without power.
Yeah, I can see that the whole thing is sensitive to the geography, because if you have a situation where the utility can turn it off right away, that changes the risk, right? And if they do turn it off, that changes the risk.
Absolutely, you may turn off the risk of having a fire from the power lines, but on the other hand, you've got a lot of unsatisfied people who don't have electricity.
So this is a complicated business, and it is geographically centered. And I just wonder, at a point in time, you left to go to the Forest Service on the mainland, and the system did not continue. The Hawaii-specific system did not continue here, apparently for the lack of scientific, staff. But isn't that something that the university should have continued? Isn't that something that the U.S. Forest Service should have continued? And isn't that something that we need now here in Hawaii?
I certainly believe that. And you know, the Riverside Fire Lab, where I spent most of my career, has actually uh, reduced its staff of fire scientists. So I was, one of two fire research, fire meteorologists at the lab before I retired. And that was in 2011. Now there are none. There are no research fire meteorologists there. And I just got an email this morning from my colleague in Riverside who said that the station the research station that I work for in California does not plan to hire any fire research meteorologists in the future. So funding has certainly impacted the research programs nationwide.
And this is a bad time to knock off that system anywhere. We're in the middle of climate change. I wonder right now in Hawaii, the guy in Kihei who had the screen showing, the interpolated data about fire danger, rating fire danger in the state, in every location in the state. He doesn't have anything on the screen, am I right? Or does he have something on the screen that's different?
He doesn't even have a system that he can go to. And that system could easily be restored, I think, provided that you bring back the expertise to Hawaii, and you not only have to bring it back, you have to grow it. And the fire science that I've been talking about is not only useful for the purposes that I described, but it's also useful in order to understand the complexities that occur between fire and the other parts of the ecosystems, whether these ecosystems are in Hawaii or any other place. And certainly,
it's part of a larger environmental problem. It interacts with the environment both ways.
And so do people. And so, you have to understand the entirety of that relationship in order to better manage the public lands for public purpose.
Well, Francis, are you ready to come out of retirement and come back and get this thing operating again? What do you think?
I would love to administer some CPR there. Okay.
Scientific CPR. You heard it here on ThinkTech. So, Francis, I want to cover one more point. We see news on a regular basis about fires around the country, especially in the West and Northwest, and it's really terrible how much acreage we lose and how it affects the ecology, and so forth. And and there are wildfires. We haven't seen wildfires like this, over the history of the country so much as we see them now. And it strikes me that when the news media gets on these fires and reports them to you, shows the firemen in the woods and doing all the things they do, they never mention that it's climate change. And I say to myself, well, the public then doesn't get the idea. They don't realize, they don't associate one with the other. Shouldn't they be associating one with the other?
Definitely, from my perspective, yeah. And let's take California again. The forests that we have here are not only appreciated for the beauty. We have great national parks here, Yosemite, for example, and it's gorgeous there. But the other aspect about the forests in the Sierra Nevada is that we also get our water from those forests. And so if we lose those forests, we have to think about what's that going to do to our water resources. And the other aspect of climate change is that, and you've heard that, for example, Lake Mead, which is the largest water reservoir in the in the country is down to record levels now. And so 7 Western states are worried about how they're going to divide the water resources that they get from Lake Mead and Lake Powell.
Yeah,
And
including the Colorado River Basin. I don't know what the ecology is and what feeds into that, but that affects agriculture in the West. And those are the foods that we import to Hawaii in large part. So when you talk about the diminution of the water levels in the West, you're talking about something that does affect Hawaii, right?
exactly. Well, I mean, you know, California being the economy that it is, the largest state economy in the nation, is important to the rest of the country for a variety of reasons. But it even in Hawaii, if we just look at Hawaii uh, uh, in and of itself, it's important that we pay attention to what happens to wildfires in Hawaii.
Yeah, it's very troubling to your point about the wildfire has an effect on the water levels. And I suppose, am I right? The water levels also have an effect on the wildfire. In other words, if a given forest doesn't have the same level of water that it had before, it's more likely to burn, and especially in hotter weather. And then, of course, if the fire is burning and you don't have water to put it out, then that affects the management of the fire also. So it's a two-way street. Am I right?
Well, the ecology of fire is complicates the management of wildlands. That's for sure. Because in Hawaii, in particular, a lot of the problems occur in grasslands, and Hawaii, unfortunately, is home to exotic grasses that have managed to do okay in fires. That's not the case for native vegetation.
Mm.
So when we get fires in those types of grasses, they do all right, but the fires uh, otherwise would help the exotics to replace native vegetation, and that would be unfortunate.
One very interesting point that came up during the Trump administration was that there was a fire, and Trump blamed the fire management authorities and the state authorities. I forget what state it was, for not clearing the underbrush under the trees, and the press was really quizzical about that. Are you serious? Is that really what happened here? And could you minimize the danger by clearing the underbrush under the trees? Or if not, and this is my question, because I don't take his comments seriously, but my question is, what can we do looking forward now, today, to reduce this danger, this risk? I mean, is there any step that the community, the state, the county, the country can take to minimize the risk?
Well, I think that one of the tools that, unfortunately, in California, we're hesitant to use is prescribed fires. That is to say, planned fires, which we can execute under conditions, weather conditions, and fuel conditions that we select instead of wildfire selecting. And the reason you would want to do that is because you want to reduce the fuel loads, particularly the dead fuels that naturally occur in forests and wildlands, just because vegetation grows and dies. So over time, you have accumulated dead vegetation, which in itself would create a fire hazard. And my major professor at UC Riverside, where I did my PhD dissertation, did a lot of research comparing fire patterns in Southern California versus Mexico. So these areas were in relative proximity to each other. And he concluded that we did too good a job of fire suppression in places like California, so that what happened was the vegetation was allowed to grow and accumulate, and that would lead to conditions that would, in fact, promote severe fires, as opposed to Mexico, where they just let things burn. And so that left a mosaic that mitigated really disastrous fires.
Well, making an intentional fire to limit the risk going forward is a dangerous business. I recall it was not too long ago, a year and a half, where some fellow did that. He started a fire as I don't know what you call it, a backfire, preventative fire, and it got out of control. And it became the source of huge forest fire because he didn't do it quite right. So, that's the science in itself, isn't it? To figure out, maybe using that same data that you were talking about, the fire danger rating system, to be sure that when you set a preventative fire to burn the underbrush, whatever, you do it in the right way.
Yeah, you would not use the fire danger rating system. You would use this other system that I was talking about, which is the fire behavior modeling system. So we have this system called Farsight, which does exactly that. And in fact, you can use this Farsight modeling platform. You would need high resolution weather data to drive it as well. To do some planning as to how best to use the lands that you have, whether or not you should be putting development into a wildland area, because the weather and the climate and vegetation tells a lot about the fire potential in any given area. So it's best to look at those factors while you're considering what to do with any lands that you manage.
Francis, I'm sorry we won't be able to get to all the other slides you had. You had quite a few. But I want to ask you this question. I mean, where can people learn more about wildland fire science ratings? Where can they learn about it? Where can they learn about your particular science, your model, and what should be done?
Well, I would start just in terms of learning about wildland fires in Hawaii. There's a nonprofit in Kamuela called the Hawaii Wildfire Management Organization, and so they take a broad-based approach about the wildfire problems in Hawaii, in concert with not only public agencies but also private organizations as well. So that's a good source for information. Other than that, I think we need to bring back fire science to Hawaii.
Okay, we're going to leave it there. We need to bring back fire science to Hawaii. Francis Fujioka joining us from Oxnard and hoping to come back. At least I hope you should come back. Thank you so much, Francis.
Aloha, Jay.
Thank you so much for watching ThinkTech Hawaii. If you like what we do, please like us and click the subscribe button on YouTube and the follow button on Vimeo. You can also follow us on Facebook, Instagram, and LinkedIn, and donate to us at thinktechhawaii.com. Mahalo.